It's now time to move on to our next speaker, Duk-Yong Choi from Australian National University, to talk about applications of few layer metasurfaces in free space optics, filtering, and polarization control. So Duk-Yong, I invite you or welcome you to the virtual stage, please.
Hi everyone, I am Duk-Yong Choi from the ANU. So today my talk is on pure layer metasurface. So my pointer here. So in the last few years, metasurface has been a quite burgeoning field of research, and they are nanostructure array with a sub-wavelength period and sub-wavelength thickness. So normally it composed of a single layer patterning with a single material. So it is easy to fabricate. Therefore, it could replace a bulky optical component. So metasurface can function as almost all the other optical elements can do. So wavelength filtering, such as color filter, wavefront control, like lens, and polarization control, such as vortex beam generation, and making new color using materials nonlinearity. However, sometimes single layer or single material is not enough in terms of efficiency, controllability, and functionality. So in this context, I will present what I have done with my collaborators to overcome such drawbacks using pure layer metasurface. Okay, so aluminum nanopattern was used as a spectrometer in visible range. The structure is bottom aluminum reflector and top trapezoidal aluminum and silicon dioxide interlayer. So due to the gap plasmon and its angle, diffraction angle dependence with wavelengths, the diffracted light comes out of different angle at different wavelengths. So it is a kind of reflection type prism. So we stacked another aluminum trapezoidal to extend the spectrometer range from visible up to near infrared. So it is a two-layer metasurface. So the structure is a little bit bigger near infrared antenna and top visible antenna with the silicon dioxide interlayer. So similar aluminum plasmonic project, we produced a bilayer aluminum nanorod separated by 100 nanometer thick SUA polymer. So this bilayer aluminum nanorod has polarization dependent transmittance. So compared to single layer structure, double layer structure has a much wider transmission, a wider operation wavelength range, and high efficiency. So this could be used for grayscale imaging by just changing the nanorod orientation, and polarization encoded imaging. So some single pattern show different images at different polarization. And another example is optical anti-counterfeiting by using polarization conversion. So, okay, so next, dielectric doublet metasurface. So compared to previous metal nanostructure, dielectric structure have big advantage of low optical loss. So in this project, amorphous silicon nanostructure were patterned on both sides of glass substrate and utilized as solid state beam scanner in LiDAR application. So this is quite labor intensive structure. It is not only composed of 2 times nano patterning on both sides, it also needs a very careful sample handling without damaging predefined pattern. Also, exact aligning of 2 metasurfaces through 1 millimeter thick glass substrate. So I use transmission optical microscope for this alignment, and the accuracy is around 10 micron. So we designed 2 metasurfaces imitating convex lens and concave lens. By carefully choosing structure width, we achieved the phase profile of Fresnel convex lens and Fresnel concave lens. So therefore, the light is converged first by convex lens and then diverged by concave. So using this measurement setup at 1550 nanometer, we could achieve wide beam scanning angle just by tilting this doublet. Here, the exit angle of light is 3 times of incident angle. Then we integrated this doublet on top of silicon nitride waveguide with grating couplers. So light propagates along the waveguide, then emits upward at the grating. So by scanning the wavelengths, we can steer the beam from here to here. So without this doublet, the steering angle is only 7 degrees when the wavelength scanning range is about 100 nanometer. However, this doublet could amplify the angle by 3 times bigger. Also, by switching from this port over this port, we achieve another 2-fold enhancement of the scanning angle. So this could be a very good news for compact solid-state beam scanner in light application. So using Metasurface doublet, we made flat retroreflector. So retroreflector is a device to reflect light back to its origin, regardless of its incidence angle. The structure is 1 micron tall amorphous silicon nanopillars on front and back surface. This is for convex lens, and this is concave lens, and aluminum reflector on the back. The thickness of this silica substrate should be carefully chosen, exactly matched with the focal length of this concave lens and convex lens. So we use this little reflector in free space optical communication. We send the 0101 signal at 1550 through this little reflector and detects them at different reflector tilt angle. As you can see here, the reflector can operate up to 25-degree tilt angle. Also, the performance is still quite satisfactory at 9 gigabps data rate. So another type of fuel layer metasurface. So most metasurfaces are using single material. For example, titanium dioxide nanoparticle array reflect green light, but there is also some minor peak from high order mode. So as a result, the color is not pure. So we designed multidielectric metasurface to reduce the high order mode. So in the structure, titanium dioxide is sandwiched by silicon dioxide on top and silicon nitride on bottom. So each layer acts as some index matching. So this SEM image shows the 3-layer nanopillar on glass. So silicon nitride, titanium dioxide, silicon oxide were successively deposited on the glass substrate, then etched at a time in CHF3 plasma. And this is observed colors. So color change with each period and gap between nanopillars. So as you can see, the color is very bright and highly saturated color, covering very wide color map. So in this talk, I introduced several examples of few layer metasurface, stacked aluminum nanostructures, amorphous silicon doublets, and titanium dioxide-based high purity color filters. So I believe pure layer metasurface could overcome the limitation of a single layered or single material metasurface and enhance device efficiency, controllability, and functionality. And that's it. And thank you for your attention.